The question of evolution has remained since it has become a theory. The question being whether or not evolution actually happened, or if there is simply a God who created our world. When this idea was first thought about in the theory of natural selection in the 1830s, most were still very for a God, causing controversy within the world. However, in our current day and age, science has become more and more prominent as the theory of evolution looks more and more likely to be the reality through our many discoveries. One discovery that has brought about the confirmation of evolution is that of transitional fossils. This is any fossilized remain of a life form that exhibits traits common to both an ancestral group and its derived descendant group. Thus, many transitional fossils have been found, such as the Sarcoptergi, Myosids, Acanthostega, Ichthyostega, Archaeopteryx, Tiktaalik, and most importantly, Australopithecus, that helped the world understand how evolution wasn't like a staircase, but more like a tree of life. Sarcoptergi are a type of transitional fossil which were dominant in the early to mid Devonian seas. They were bony fish with lobe-paired fins, which were joined to the body with a single bone. You can find them right here on their phylogenetic tree. As well, they have two main lineages, the coelacanth, which are actually still alive today in our oceans, and the Rhapidistia. The main difference between the two is that the coelacanths remained in the ocean while the Rhapidistia moved to freshwater to avoid selective pressures and predators. However, they are no longer alive today, for they split into two lineages as well, lungfish and Tetrapodomorphia. In fact, lungfish evolved the first protolungs and protolimbs, and they adapted to use their stubby fins or protolimbs to walk on land and find new water if their water hole is depleted. And they can also use their lungs to breathe air to get sufficient oxygen. As well, the Sarcoptergi were much more closely related to mammals than other fish, and because of their fin-like limbs, they are considered the ancestors of tetrapods. Thus, they show one of the first limb-like structures, the transition from fins to limbs, and the evolution from saltwater to freshwater. They are very important. And like I said, the only difference is one lives in the ocean and one lives in freshwater. As for myosids, they were the first wave of mammalian carnivores and were found as fossils in deposits 65 million years ago in North America and Europe and Asia. They were evolved after an asteroid obliterated the dinosaurs and left numerous ecological niches wide open. With dinosaurs gone, mammals were able to start taking over. Myosids were roughly the size of house cats, were covered in fur, had tails, elevated metabolisms, and were one of the first to develop teeth for tearing meat. Some were probably forest dwellers as well, preying on smaller animals, while others were arboreal, leading to the two groups in which they divided as evolution occurred. The first group was Myosidae, which evolved into the caniforms such as bear dogs, raccoons, bears, and weasels. And the second group was Viverridae, which evolved into feliforms such as cats, hyenas, and mongooses. Ergo, myosids demonstrate the evolution of the very first animals to more modern-day mammals. Here is a picture of one showing the sharp teeth to tear and chew meat, which is a very prominent feature. Its tail, its fur, long ears to pick up slight movements, sharp claws to inflict a lot of damage. Next, we move on to the Acanthostega and the Ichthyostega, which are, as seen on the phylogenetic tree, they are both very, very closely related, but there are some differences. First, there's the Acanthostega, which are animals very similar to modern-day crocodiles, which are a 360 million year old ancestor of land vertebrates. They lived in shallow water environments, and the size and distribution of its teeth and the shape of contacts between individual bones of the skull, called sutures, suggest Acanthostega may have initially seized prey at the front of its jaws using its large teeth and hook-shaped lower jaw. And it's also very unlike anything we know today. They had 8 fingers and toes, for they were transitioned from fish to tetrapod. This is also known because of their combination of fish-like and tetrapod-like features. Acanthostega had gill bars like a fish and no true elbows, knees, wrists, or ankles, and they were not weight-bearing at all. They also have long fin rays around the tail. Nonetheless, they had a head that was not joined to the shoulder girdle, an ear bone which fit into the fenestra in the brain case, a large pelvic girdle and sacral rib, a femur as large as the humerus, a tibia and fibula attached to the ankle bones, and digits on each limb, just like a tetrapod would. This very nicely shows the transition, another branch on the tree of life, of fish to tetrapods. Next, we have the Ichthyostega, which was roughly 4 feet long, primarily aquatic version of the Acanthostega. Its forelimbs were weight-bearing, but forearms could not extend fully, so it was like a seal pulling itself with forelimbs and dragging its back onto the land or shallow depths. The back legs were smaller than thought, though, and is now thought that they served as paddles rather than legs, which is just further proved through its 7 toes, because you can't walk with 7 toes. Furthermore, its ribs, which are narrow both proximally and distally, broaden dramatically in the middle and extensively overlap adjacent ribs. This was believed to help support the trunk while it was not buoyant in water. As well, dramatic longitudinal differentiation of the spine was found in other reptilians during the Permian and Triassic periods, but was not expected to be found in tetrapods, once again showing the transition between these two creatures. It also had a pelvis, which was large and attached to its spine, and recent investigations on the otic chamber suggest that Acanthostega had a uniquely specialized ear as well that may have used air chambers as underwater sound transducers. However, no evidence for postbranchial lamina has been found, which suggests that it may have lacked internal gills a typical fish would have. All in all, Ichthyostega and Acanthostega have been recovered from within the same deposits, but not from within the same horizons. The temporal and ecological separations between these two early tetrapods is very unclear. Skeletal differences between Acanthostega and Ichthyostega suggest that they had rather different life habits as well. It's been speculated that Acanthostega was probably exclusively aquatic, while Ichthyostega may have hauled itself up onto shore sometimes. So not only does the Ichthyostega show a small leap towards land, it also shows how speciation occurs. Next we have Archaeopteryx. The Archaeopteryx was discovered in 1860 and was named with a combination of 2 ancient Greek words, archaeos meaning ancient and pteryx meaning feather or wing. Thus, it survived 150 million years ago in Bavaria, Germany, and was 1.8 to 2.2 pounds. It had a tail which could be up to 50 centimeters in length and had hair like proto-feathers. In spite of that, though, they had no feathers on the upper neck or head regions, and it has not been yet discovered as to why, but the feathers do suggest a strong connection to modern-day birds. All the same, their claw structures suggest it wasn't climbing or perching on trees. Thus, they likely had some aerodynamic ability, but had a primitive shoulder girdle, so flapping would have been difficult. And so it probably lived in open space with few big trees for gliding in the air. Although these traits that make up the Archaeopteryx, which represents the transition from dinosaurs to modern birds. This would roughly be what it would look like, with its beautiful feathers open. Next unearthed in Arctic Canada in 2004 was Tiktaalik. Tiktaalik is a fish from 375 million years ago, which lived in shallow water where it could prop itself up to grab its prey. This creature had a massive pelvis compared to other lobe-fin fish, which meant they could grow up to 9 feet long. Moreover, it was only technically a fish with its scales and gills, but it had a head like a crocodile and unusual fins, which allowed for standing like 4-legged creatures. This, all along with its distinct neck, suggests that it was the beginning of a transition to tetrapods. Again. In fact, it could walk underwater. How could it be that, along with Tiktaalik, was also Ichthyostega, Acanthostega, and Sarcopterygi, all of which were on their own paths to walking on land? Evolution, maybe? Finally, we have the Australopithecus. These are one of the first bipedal creatures known to date. Firstly, we had the Australopithecus anemesis, which lived 4.2 to 3.9 million years ago in eastern Africa. This was first discovered in 1995. It mostly ate seeds, sedges, grasses, fruits, and tubers. This is an appetite much like that of modern baboons. Secondly, there is the Australopithecus afarensis, which lived 8.5 to 2.5 million years ago, also in eastern Africa. Sorry. They grew rapidly after birth and reached adulthood earlier than humans do in modern day, although they also had ape-like face proportions such as a flat nose or strongly projected jaw, and a brain case which was 1/3 the size of a human brain. Furthermore, they had strong arms with long fingers for climbing trees and small canine teeth for other early humans. Males were an average of 4 feet 11 inches tall. Female average 3 feet 5 inches. So there was a huge difference in size. There's the Africanus. This was discovered in 1974. Finally, there was the Australopithecus africanus, which lived about 3.3 to 2.1 million years ago in southern Africa, meaning there was a migration of the Australopithecus at one point in time between the afarensis and africanus. They also had a rounder cranium, which housed a larger brain and smaller teeth, showing how they evolved from one to another and from apes to eventually humans. One amazing discovery of the Australopithecus was Lucy, who was named after the Beatles' song Lucy in the Sky with Diamonds. She was found in 1974 in Ethiopia, where 40% of her body was recovered, which was an amazing feat for the science world. She was 3.5 feet tall and was about 65 pounds. Very small compared to modern-day humans, if you think about it. Her third molars, or wisdom teeth, were erupted and slightly worn, indicating that she was fully adult, but a younger adult, and furthermore, all the ends of her bones had fused and her cranial sutures had closed, indicating completed skeletal development. The shaft was also angled relative to the condyles, the knee joint surfaces, which allows bipeds to balance on one leg at a time during locomotion. There was a prominent patellar lip to keep the patella or the kneecap from dislocating due to this angle. Her condyles are large and are thus adapted to handling the added weight that results from shifting from 4 limbs to 2. So she could have walked on either all 4 limbs or 2. Imagine the advantage she would have being able to do either. The pelvis exhibits a number of adaptations to bipedalism as well. The entire structure has been remodeled to accommodate an upright stance and the need to balance the trunk on only one limb with each stride. Moreover, the talus in her ankle shows evidence for a convergent big toe, sacrificing manipulative abilities with the toes, such as we've seen with apes, for efficiency in bipedalism. Finally, the vertebrae shows evidence of the spinal curvatures necessitated by a permanent upright stance. So not only do Australopithecus show the advancements to humans, but also to bipedalism. So, which is right, the staircase or the tree? All in all, these 7 transitional fossils show different transitions between an ancestral group and their descendants, as well as the advancements these creatures made to survive and be selected for. All this helps us understand evolution on a grand scheme of things as more of a tree rather than a linear progression. So hopefully, as we move through life, more transitional fossils can be found or finished to finally aid us in completely understanding how we got where we are today. How we went from this base of the tree, this one fish, and it just spread out in multiple different areas covering all the ecological niches to get us where we finally are today.